Water walls. A water wall is a layer of water wrapped around the spaceship. It's likely less than a foot thick and is good for solar particle events, known as SPEs, which are generated from solar flares and coronal mass ejections. It's not good for galactic cosmic rays, however. We'll talk more about that later. For the water molecule, H2O, right, it's that simple. Not really. Let's break it down a little further. We have a proton and an electron for each hydrogen atom with their designated charge, right? Positive 1 for the proton, negative 1 for the electron. Adding those two together make it neutral. The oxygen atom is atomic number 8 on the periodic table. So it has 8 protons and 8 electrons. But I often forget about the 8 neutrons that in combination make this nucleus bigger. Note that the hydrogen atom doesn't have a neutron. That's important here for this exercise. Also note that I haven't broken the electrons into their shells. It doesn't really matter for this exercise. I know some people will be bothered by that, but when you're messing with all these particles, it doesn't really matter. Let's impact a target. So what we have here is protons in green. They're the green peas. Neutrons are the yellow corns or corn kernels. The electrons are black peppers, little peppercorns. And we won't use this in this instance, but we have iron nuclei, which is a blueberry. So solar particle events are also known as solar proton events. That's because mostly it's comprised of protons. So we'll use a proton in this case to impact a water molecule. So here's our proton. And let's say it makes impact with the oxygen atom. And it kicks off, say it kicks off, I don't know, maybe a proton and a neutron. So we have our primary particle here, a primary projectile, a secondary projectile, because it's moving pretty fast. It was hit with really good energy, and so it has really good energy. And we have a neutron that's moving pretty fast as well. So all three of these things, as well as electron, depending on how it played in it, maybe that lone electron that got kicked out has some energy, and if it does, it's a beta particle. Electrons are also known as beta particles. So we have all these things flying down through the water wall and looking for their next impact. Let's say we go 100 molecules down and we find another impact. And in this case, our neutron hits this hydrogen atom, kicks it out. Guess what? It's radiation now. It's ionized. It doesn't have its electron. Electron is free floating or moving fast as well. So the whole idea here is high energy particles, projectiles, moving and making impacts. I'm not tracking any energies here, but as they impact, they lose energy. And the more impacts they have, the less energy they have. And hopefully when they get to the end of the water wall, they are sufficiently low energy that it's not going to do any damage to the human being. So that's the idea here. Let's talk about design. Designing your target space. Maximize your impacts minimize your secondaries. That's the key. As you can see, the oxygen nucleus presents a lot more targets than the hydrogen atom, particularly neutrons. Looking at lead, it has 82 protons and 126 neutrons. It's good for X-ray protection, but not SPE or GCR protection. There are too many secondaries that are produced. Now the best passive shield would be all hydrogen atoms, right? So how could we do that? Well, a gas isn't very dense, so you don't want hydrogen gas. We do liquid hydrogen, but liquid hydrogen is cryogenic. You have to cool it down below, I think it's 20 Kelvin. And so to do that, you've got to have some complex thermal management system that that would be difficult to do to keep the system cool enough to keep it liquid hydrogen. So what we do is talk about water, a couple hydrogens there, high density polyethylene, that's a C with two H's as well, so it's very similar to water. It's bonded with another C and two H's. But yeah, that's the best you can do with passive shielding. So that's why we look at water walls as one way to protect the crew. 1 foot of water is very heavy. I probably ought to do the calculation to see what that looks like. But that's the discussion on design. Let's talk about transforming. Let's look at GCR going through our water wall. That's galactic cosmic radiation, a lot higher energy radiation. I'm not keeping track of the energies of every impact, but let's say we have a 500 GeV iron nuclei traveling through through our water wall. 500 GeVs. It's known that you can get up to 1 TeV, but GeVs very common. We're talking about giga electron volts, and again, this is just an energy unit, and it's associated with velocity. So let's say it makes 5 or more impacts before exiting the water wall. The energy drops off after every impact. The angle that impacts plays a part in its drop in energy. And in the end, after that many impacts, the particle flies through the wall with ease. Let's say we have a blueberry, which is our iron nuclei, and this blueberry or this iron nuclei comes in and impacts the oxygen. And it's not uncommon for an impact to release an alpha particle. An alpha particle is a helium nuclei. So it's number 2 on the periodic table. So it has +2 charge, because it doesn't have its 2 electrons. And so these electrons are free-floating electrons that are beta particles. And if they have velocity, they could become a radiation of concern. So we hit the oxygen atom, and we continue to move on. Let's say it goes through 100 layers of molecules, and it comes across another proton, and that's really a hydrogen nuclei, right, or a hydrogen atom, and it splits the proton from its electron, and it just keeps going, right, and it keeps making a mess of things, and it keeps making impacts, and it keeps lowering its energy. Well, GCR has too much energy for this water wall. It's going to go right through the water wall, and it's going to possibly go impact a crew member. And so um, we're talking about needing yards of water to put on the habitat or the spaceship to protect the crew. No one will launch the Gulf of Mexico to shield the radiation. But to get back to where we started, we're looking for transformation. We're looking to transform the high energy particle to a low energy particle. And while you're at it, you need to transform the higher energy secondaries into lower energy secondaries, so when they enter the crew module, they don't cause a problem. And that's transforming radiation. At the cell, we've seen what solar particle events, SPE, and galactic cosmic rays or radiation, GCR, do to matter. It bangs it up. But what happens when it hits the body? When it hits a cell, you hope that it kills the cell. Your body knows what to do with dead cells. It's the damaged cell that you have to worry about. It splits to make two new damaged cells in this situation and turns into a tumor over time, cancer. So that's why astronauts on the space station stay for usually no more than a year. That is about the time when they reach their dose limits and it's time to come home. Conclusion. Let's wrap this up. In review, the water wall works very well for solar particle events. However, it creates secondary radiation, even though it's been minimized by using water or using high-density polyethylene. The only way not to create secondaries is to have a magnetic field without any structure or passive shielding. We need to build a magnetic field around the spaceship strong enough to turn SPE and maybe even some of the GCR. We can't turn all GCR. The field strength is impossibly large. The allowable dose gives the crew better than a year mission. Propulsion has to fill the gap by shortening the mission duration to go to Mars.